this tutorial on word embeddings and Word2Vec. In this session, we will learn about the need of word embeddings, understand Word2Vec, explore the mathematics behind it, and implement it in Python. And I will also show you how word embeddings look like in 3D space. So the topics to be covered in this video are word embeddings, and in this we will get the intro of word embeddings and see how we use it, why we use it. Then we will move towards the introduction of Word2Vec, and we will cover both approaches of Word2Vec, which are continuous bag of word and skipgrams. And we will see the mathematics behind it. We will get the mathematical intuition behind Word2Vec, how it works, and how these word embeddings are trained. Then we will implement it with Python. Then we will see the 3D visualization of Word2Vec word embeddings using a tool. So now let's get started with the introduction of word embeddings. So word embeddings, the first question that comes to our mind is, what's wrong with the traditional text representation methods? So before word embeddings, traditional methods like one-hot encoding and TF-IDF, one-hot encoding and TF-IDF were commonly used for text representation. However, these methods have several limitations. So let's see what were the limitations of one-hot encoding. So in one-hot encoding, what we did was, in one-hot encoding, we were representing text in the form of vectors. But the method of one-hot encoding was, we were representing, if our data, if our document has, let's say, 10K unique words, then we have to represent every word in the document with 10,000 dimensional vector. This means it is taking too much space. One-hot encodings were taking too much space, and with this high dimensional vector, our computation cost was too high, and the vector representation was sparse, which means it is including lots of zeros, which means let's say we have 10,000 words, so nine we have only one dense representation, and all the other representation were in the form of zeros. So which means most of the values, or we can say 99% of the values of that vector are not useful for us. So this is one hot encoding was the sparse representation of words. uh, each word is represented as a unique vector, but it fails to capture the semantic relationship between words, and the vectors were sparse. So if you let's take an example. Let's say we have two words in our data, cat and water and dog. Let's say we have three words. So we have three words. So now let's say we have to represent it using one hot encoding. So we will the encoding of cat will be 1 comma 0 comma 0, and the one hot encoding of dog will be 0 comma 0 comma 1, and the one hot encoding of water will be 0 comma 1 comma 0. So if you see these vectors, they are converting text into vectors, text into numbers, but they are not showing any relationship between these words. Although dog and cat are related to each other because they both are animal. But this vector representation is not representing that relationship, and dog and water are not similar, but this representation is not showing any information about the similarity, about the relationship, context, and semantics of the word. Then we have TF-IDF. Then we have TF-IDF, turn frequency and inverse document frequency. While it improves over one-hot encoding by considering word frequency, it is very useful for text classification tasks, because it focus over the word frequency, but it still does not capture the meaning of context, the meaning or context of word. Which means if you will see the representation, let's say the representation is 1 comma 0 comma 9, but this representation is only telling us about the frequency of word in the document. in the document, but it is not telling anything about the relationship, semantic, or context of the word. So we have to solve these problems. Then word embedding comes into the game. So how word embedding fix these issues? Word embeddings provide a dense. Let me erase this. Word embedding provide dense, lower dimensional representation where words with similar meanings are positioned closer in the vector space. So the first thing is it provide dense representation, which means if you see one hot encoding, if you will see one hot encoding, the representation were like 1 comma 0 comma 0 comma 0 comma 0 comma 0 comma 0. So only this value is of our use, but all the other values are trash values, are garbage values. These values are not representing anything, and they are taking more space in the memory, and they are causing trouble in computation. But in word embeddings, we will represent these elements with dense vectors like -1, 0, comma 9, 0, comma 8, 0, comma 7, 5, 0, comma 3, 0, comma 1, like this. So this is the dense representation, and every value, every element is representing something. So we are not taking. So this is computationally less expensive, and this will give us more information about the word and its context. The second thing is it provides the lower dimensional representation. Lower dimensional representation. So what does this mean? So in one hot encoding, in traditional word representation technique like one hot encoding, we represent words with n-dimensional vector, and uh, this n-dimensional means the number of unique word in the sentence. So let's say we have a document of 1 million words. So we have to represent every word with 1 million dimensional vector. 1 million dimensional vector. So this will take too much space. Too much space. This is very costly and not efficient. So we have found the way to represent every word with lower dimensional, which means we can select dimensions by ourselves. So in word embeddings, we select dimension by ourselves, so we can represent any words with any dimension. Let's say we have 300 dimensional vectors, we have 512 dimensional vectors, we have 1000 dimensional vectors, and so on. So we can manage these dimension with ourselves. Now, uh, this helps capture the semantic relationships and contextual information, making them far superior to traditional methods. So also this representation is capturing the semantic meaning of word and the context in the context that word is used. So if you will see here, this is the example of word embedding. So in word embeddings, we convert word in the form of vectors. So if you will draw a 2D plane, so let's say we have two words, uh, cat and dog, and water. So we know that a cat and dog are similar, but water is different. So we will find a way. Let's say so in word embedding, the vector representation of cat and dog is similar, but the vector representation of water will be different. Which means if you will draw it on 2D plane, so let's say cat will fall somewhere here, and dog will fall somewhere here, but water will fall here, because water is dissimilar with cat and dog, and cat and dog is similar with us. So if you will see, the distance between cat and dog is less, but the distance between cat and water is too much. This represents the context and the semantics of words. We have solved three problems using word embeddings. First is we are representing words in dense vector, which means we have no garbage value in our vector. And the second is we are capturing the context and semantics of word. And the third is we are reducing the dimension, which means we are doing dimensionality reduction here. So we can represent it in less dimensional vectors, which will be cost effective and easy to compute, easy to calculate, and easy to understand. Uh, Now, these are the examples of word embedding. If you will see here, this is the sentence. Mathematics is similar to statistics. So the mathematics and statistics, these two words are much closer than the words mathematics and tiger. And tiger and lion, these two are animals, so they are in the same group. And these are the subjects, so they are in the same group. So we can represent, so this is for understanding, but this is for understanding. We are using 2D plane here, but these word embeddings can be of 100 dimension, 300 dimension, or 512 dimension. So that will be not easy to visualize. So at the end, we will see a visualization tool for that to visualize word embedding, especially Word2Vec model, uh, and we will visualize it using a tool, and we will also see two dimensionality reduction techniques, PCA and TSNE. So now let's see what is Word2Vec. So Word2Vec is introduced by Thomas Mikolov. So this is the original paper. This was developed by Google workers, Google engineers. So this was the original paper of Word2Vec model. In this, they have described everything about Word2Vec, that how they made it, what approaches they have used, and what is the use of Word2Vec model, and everything about Word2Vec. So this is the paper. I will pin this in the description. Give the link of this paper in the description so you can read it. Now, Word2Vec is it is introduced in 2013. It is a popular algorithm to learn word embeddings. It transforms word into continuous vector representation by leveraging their usage context in large corpora. So let's see. Let's now see. So Word2Vec is a word embedding technique. Word embedding technique. It is a basically it is developed by Google engineers in 2013, and it is used for learning word embeddings. And this is deep learning based approach. Deep learning based approach for training. So now let's see how does Word2Vec work. So this is the example of working of Word2Vec. So let me explain it to you first. So we have to represent, first let's see what is the goal. So we have to represent words such that the first thing is we have to convert words into numbers, or more specifically vectors. Then those vectors those vectors should be capable of holding the context, semantics of words, and we want them of lower dimensions, so that they will be easy for computation. So lower dimensions and dense vectors with less garbage values and more useful values. So less garbage values and more useful values. So now let's see. So we, in previous traditional methods, we have solved this problem, that we were easily converting words in the form of vectors in techniques like one-hot encoding and TF-IDF. But they were not capturing the context and semantics of the meaning, and they were of very high dimensions, and they were not dense, they were sparse. So now we have to solve these three problems using Word2Vec. So again, let's take an example. Let's say we have three words: cat, dog, and water. Now it is deep learning based approach, so we have to deal with features. So what Word2Vec does is it creates features of word. By feature, it means, let's say one feature could be alive, that the thing is alive or not. So cat is alive, so we will give it one. Dog is alive, and water is not alive. And the second feature could be of say, tail. So cat has tail, so we will give it one. Dog has tail, water has no tail. Now let's say the third feature can be mm, third feature can be of eyes. So eyes, cat have eyes and dog have eyes, but water have no eyes. Uh, Fourth feature can be bark. So cat can bark, no, so we will give it zero. Dog can bark, so we will give it one, and water cannot bark. So and for cat, this we can say have pause. So cat have paws, dog don't have, so we will write 0 here, and water for 0. So let's say we have another feature, flow. So cat cannot flow, so we will give 0 here. Dog cannot flow, but water can flow. Wet, so we will give 0 score to cat and dog, and for water it is 1. So now this is the representation of cat, this is the vector representation of cat, this is the vector representation of dog, and this is the vector representation of water. If you will see here, these two vector representation are more similar than this, because cat and dog have these many similar features, but water don't have these features. It can only flow and it is wet. So in Word2Vec, in Word2Vec, we define features. We define features, and based on those features, we give scores to words. Now, let's say if we have too many words, so we cannot manually give features to every word. We cannot do this manually. So we need something. We need something to generate automatic features. Here's deep learning. Deep learning comes in game. So in deep learning is a field that it deals with features. So every deep learning approach, it creates their own features, their uh, hidden features, hidden features. So now let's take this example and see what this example is saying. So yeah, we have cat. So we the one feature is living being. So cat is living being, kitten is living being, dog is living being, but houses are not living being. So we are giving the score minus 0.8. Uh, then we have another feature. Then we have another feature. Then we have another feature like gender, royalty, verb, plural, and based on these features, we are giving them scores and generating the vector representation of words. So now if you will plot them in the n-dimensional space, let's say this is a 7 dimension vector, this is 7 dimension vector, so we cannot visualize 7 dimension as humans, so we can visualize it in 3D format. So when you will plot the vector of cat and dog and kitten and house, so you can see that the vector of cat and dog, let's say kitten is here and man women are here, and let's say houses are here. So if you will see, the vector of kitten, vector of cat, vector of dog are much closer than the vector of dog and vector of houses, because this is non-living thing, and it is not similar to the other words. So as you can see here, the vector of man and women are closer than vector of man and dog, because it is a human being, and because men are human being and dogs are non-human being. So this is the approach, this is the intuition behind generating word embeddings of Word2Vec. Now before getting into the architecture and deep learning approach of Word2Vec, let's see how to implement it using Python. Now let's see how to implement Word2Vec and how to use Word2Vec model in Python. So we have a library called Gensim. So we will import gensim.api, gensim.downloader as API. So in this Gensim library, we have our pre-trained model of Word2Vec. So from that, we will download this model. So and we will store it in model variable. So we will write API dot load Word2Vec Google News 300. So this Word2Vec model, this model was trained by Google engineers on very huge data, very huge data of Google News, Google News. So it was trained on a large data set by Google engineers, and they have generated the word embeddings of 300 dimensional word embedding for every word. So now let's see. So let's download this model. So it will take some time because it is a very large model. Let it download, and let's see. So our model is downloaded. Now let's see how to use it. So to see the word embeddings, the vector representation of any word, we just have to write model, and we have to pass that word in here. So let's say we want to see the embedding of man. So this is the vector representation of the word man, and this is pre-trained Word2Vec model. So if you will see the shape or the length of this, so it is 300. So this is 300 dimensional vector. Every This model is trained to convert every word into 300 dimensional vector. So how to use this model? We have many functionalities, like if you want to see the most similar words to man, so we will write model dot most similar words to man. So it will show you most similar words to men. So as you can see, the similar words to men are women, boy, teenager, teenager girl, girl, suspected, purse, snatcher. I don't know why it is here. Robber, robbery, suspect, teenager, men. So these are the most similar words to men. So this is capturing the context of words. So if you will see here in word embeddings, it will form clusters of similar words like cities, food, body part, travel, feeling, relative. Let's say we have a man here. So in this cluster we will have women, boy, and living beings, and so on. In this, let's say we have London here. So London, UK, all the countries, cities, and related things will fall on same clusters. So now let's see most similar word for cat. So if you will write cat here, so the most similar words for cats are cat, cats, dogs, kitten, filling, beagle, puppy, pup, pet. These are the most similar word for mm, cat. So now it has many more functions, like you can check the similarity score between two words. So if you will write model dot similarity, and in this you have to pass two words like man and women. So the similarity between man and women is 28. But if you will see the similarity between man and water, it will show you 0.073. So the similarity score of man and woman is higher than the similarity score of men and water. Why? Because it is capturing the context of the word, in which context that word is being used. So same as this example, if you will write here the similarity score of cat and dog. So the similarity score of cat and dog is 76%. So as you can see, the vector representation of cat and dogs are similar, but the vector representation of cat, dog, and water is too much different. So if you will write water here, water, so the similarity score of cat and water is very low, because it is these two are dissimilar words. Same we can check for any other thing. So let's say we have a word car here and bike. So the similarity score of car and bike is 58, but the similarity score between car and dog is less than car and bike. So by this we can use Word2Vec model. So we have one more function called doesn't match. So model dot doesn't match, and in this we have to pass a list of words. Let's say we will pass cat, dog, water. So what this function will do is it will remove the odd one out. So water is odd here because cat and dog are similar, but water is different thing. Same for car. If you will write cat, dog, and car, so cat and dog are same, but car is different thing. So this is happening because Word2Vec model or these word embeddings are capturing the semantics of word, in which context these words are being used. Now uh, as I'm saying, these are the vector representation of words. So we know vectors in math, but what are these vectors in deep learning, in NLP? So vectors, these vectors are same as the mathematical vectors, which means these vectors have direction and magnitude. So we can add them, subtract them, multiply them, or we can do any operation on them. So as we can do on these mathematical vectors. So let's see here what happens if we will add two vectors and subtract it with others. So let's say we have a model dot model of vector king, and I will subtract this with the vector of queen. Add women, add with vector of women. So this will show you the vector. Let's see. Let's store this in the variable v, and let's see the most similar vector of v. So model dot most similar vector v. So this if we will add king, if we will subtract the vector of king with vector of queen and add the vector of women, then we will get women, men, widows, women, fathers, husbands, uniforms, males. So we are getting the close vectors, or so this shows the capability of word embedding and word2vec vector, that it is capturing the context of every word. So we can apply these mathematical operations on vectors, uh, and we can check the results. So this was the Python implementation of word2vec library. So you can do many things with that, like you can make some application for text classification, because it is capturing the semantic meaning, so we don't have to regenerate the uh, 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 text representation, and we can use word2vec model, and use it with any text NLP task, natural language processing task. So this was the Python code implementation for that. So what we did is we have imported the Gensim library. From Gensim, we have imported downloader class, and from downloader, we have downloaded this Word2Vec Google News 300 model and stored it in this model variable. Then this model has three. This model has is holding the vector representation of word, and every word is represented with 300 dimensional vector in this model. So now we have seen that how to use the model with Python. Now the next thing is two architecture of Word2Vec. So we have two types of Word2Vec. We have two types of Word2Vec. First is we have two approaches for training this model. So the first approach is continuous bag of word, and the second approach is skipgram. Second approach is skipgram. So let's see what is continuous bag of word approach and how we use it. So in this topic, we will see that how these embeddings are getting trained, how these embeddings are getting learned, and how our model is making these features, and what are these features and what are they representing. So now let's see what is continuous bag of word approach of word embeddings. How does Word2Vec work? So we know that Word2Vec is based on the idea that word appearing in similar context have similar meanings, which means cat and dogs are pet. This is the sentence. So we are using cat and dog in same context, that they are pet. And let's say water is for drinking purpose. So water and drinking are getting used in the same context. So it uses two architecture. This Word2Vec model uses two architecture to learn word embedding. First one is continuous bag of word, and second is skipgram. So now let's see continuous bag of word. So it predicts a target word based on its surrounding context word. So let's see. Let's first see the terminologies: target word and context word. So target words means the word for which we are uh, predicting the embeddings, or the word which we are finding word embeddings for. And context word is these words. Let's say we are calculating vector representation of pet. So the context word are these, and the target word is this. So now let's discuss the continuous bag of word approach of Word2Vec. So in continuous bag of word, um, let's understand it with the example. So let's say we have a sentence. The sentence is cat. Let's take this same sentence: cat and dog. Cats and dogs are good pet. Is our document. This is our training data, and now we have to train word embeddings, word embeddings with this continuous bag of word approach. So what we will do is we will take this is called a sliding window approach. Sliding window. So we will let's say we have to generate two dimensional embedding for every word. So we have to generate two dimensional embedding for every word, and let's say our window size is 3. So window size is 3, which means first we will cover this. So this is our window. So in this window we have 3 words: cat, dog, and cats and dog. So we have two things: target word and context word. So let's say we have to predict dog here. Let's say first we have to predict and. So for and, our input will become is this is our context word, and this is our context word, and this is our target word, because this is we have to predict this. So our training data will become is x, which means our inputs will be cats, and this dogs, and our target variable will be and. Then we will slide this window from here to here. Now we have target variable. This target variable is dogs. So dogs are target here. So we will write dogs, and R will become the context word here. Then we will slide this window further like this, and this is our context word, and this is our target word. So good good is good target, and R and pet are uh, word. Then we will slide this further. So this will cover these two words and this word. So for this part, this will become the target word. So pet, for that we have good and cat. Then cat will become the target word. Then we have pet, and so this is our training data. This is the training data, and now we have to. This is a simple prediction task. So we can use this data for making prediction using deep learning model. So we will use ANN, artificial neural network, here for prediction. So first we have input layer. So we have two input in every word. So we have to take two input layers and one one hidden layer. So this the dimension of this hidden layer determines the number of neurons in this hidden layer, determines the dimension of word embedding. Now we need two-dimensional word embedding, so we will take two neurons. So in this hidden layer we have two neurons, and here we have our input words. So this is let's say we are sending this first batch to our training data, to our model. So here we will pass cat, here we will pass dogs, cats and dogs, and now uh, we will pass these words in this hidden layer, and then this hidden layer will uh, predict the output. So the output will be like here we will add a softmax layer. So softmax layer will give the probability for each word. So how many number of unique words we have? 1, 2, 3, 4, 5, 6. So we have 6 unique words. So we have 6 neuron in our output layer. 3 to 5, 1, 6. So this is our softmax layer. Softmax layer. So we have 6 neuron, because this neuron, every output of every neuron is the probability of every word. So after that, this will be connected to every neuron. This hidden layer neuron will be connected to every other neuron. So now we this will give the output in the form of probability. Let's say 0.8, uh, 0.8, 0.1, 0.1, 0.1, 0.2, 0.001, 0.003, 0.11, like this. And so our target word is and. So let's say the probability of end is highest. Let's say this is 0.8. So probability of end is highest, and this model is trained perfectly, and this model is accurate. Now, where we will find the embeddings of this word end. So after completing the training process, we will find the embeddings here. So let me give you a clear understanding. So we have a diagram here. So let's say we have a target word here, and these are the input word. So we will find the embeddings in the hidden layer, output of hidden layers, which means we will find the embeddings here. So if you will see, this is the hidden layer, and this is the softmax layer, and this softmax layer have nine neurons, six neurons, because we have six unique words. So let's say first unique words is cats, then we have ant, then we have dogs, are, pet. Uh, this uh, this model is now fully trained. Now we have to check the embedding of cats. So where we will find the embedding of cat? So the embedding of cat is here in these weights. So this W1 and W2 is equal to the embedding of cats. So cats will be equal to W1 comma W2. So after the training is completed, we will find uh, our embedding in the weights of hidden layer, in the output of the hidden layer. So this is the continuous bag of word approach for training Word2Vec model. Now let's move forward and see the skipgram technique for Word2Vec. So what we do in skipgram, we just reverse the architecture of previous approach, which is continuous back. So this time we will reverse the problem and reverse the architecture. So our data was this. Our data was this. Cats are this was our data. So let me copy it from here. So this was the training data for continuous bag of word. Now we have to reverse this data, which means this y will become x and this x will become y. So now we have to predict the context word for every target word. For target word, we have to predict the context word. So we will reverse the architecture, reverse the previous architecture, this architecture. Now we will pass our target word here, and then pass it to the hidden layer, and then it will predict the context words. So let's say we are predicting four context word. We have a sliding window of size 5 or 4. Uh, so we have these context word. We are predicting these context word based on this uh, target word. So this time the embeddings will be here between the hidden layer and the target word. So let's draw this architecture. So we are passing our target word from here. So we will pass every target word from this input layer, and this hidden layer is of two-dimensional neurons, because we want two-dimensional embedding. And then we have to predict target word. So we have to predict two target word every time. So this will be like this. So this is our softmax layer. This is hidden layer. This is input layer. So this time the weights or the embeddings will be here. So let's say this is the first word, cats. So the embedding of cats will be W1 and W2. So the embedding of cats will be W1 and W2. So this is how we train a Word2Vec model using these two approaches: continuous bag of word and skipgrams. Now let's take the original example of Word2Vec model. Uh, in Word2Vec, Google, they have trained Word2Vec model for 300 dimensional data. So for training 300 dimensional embeddings, we have to increase the size of this hidden layer. So let me show you in continuous bag of word. So we have to increase the size of this layer, this hidden layer. So if we want the embedding of 300 dimensional, so we have to increase the size of this hidden layer from 2 to 300. So this size will tell you that how many dimensional embeddings are generated in this model. So we have solved every problem using word embedding. We are capturing the semantics, we are capturing the context, These are dense representation and lower dimensional embeddings. We can manipulate dimension with ourselves. We can increase or decrease the size of dimension as per our need. So this is the this is how Word2Vec works, and this is the mathematical and deep learning based intuition behind the training of Word2Vec models. Now, uh, now we have generated 300 dimensional embeddings. 300 dimensional embeddings, but we cannot visualize three-dimensional space. We can only visualize three-dimensional 300 three-dimensional space. We cannot visualize 300 dimensional space. So how we know that what words how words are looking in this 300 dimensional space? So for that we need a visualization tool. So now let me show you the 3D visualization, 3D visualization of Word2Vec word embeddings. So this is the tool for visualization of word embeddings using PCA and TSNE. So PCA and TSNE are dimensionality reduction techniques. PCA stands for Principal Component Analysis. So as you can see, these are the word embeddings of word. So let me show you for all words on which Word2Vec model is trained by Google engineers. So it is loading. It will take some time. Is computing PCA, reducing the dimensions of these. So these are the full word embeddings of Word2Vec. These are the generated word embedding of Word2Vec. So if you will see here, this is PC cursor. So all the related words are in the same cluster. If you will see, let's say here, gadget, digitally, images, customizable, slip. All these similar words are in same place. So this is the vector representation of words. You can also convert it into word format. So these are the words, and also you can visualize in the dark theme. Now let's say we have to search a word. So we have to find this word king. So the related word to king are kingdom, making, working, talking. Sorry, we have to, let me show you this word. So these are the similar words in the cluster. Now if I will write queen here, have queen, and we have nearest point to the original space, which means these are the related words. These are the similar words as queen. So we have Elizabeth, king, Mary, and this is the similarity score that I have shown here in this Python code. So if you want to visualize word embeddings, Word2Vec word embeddings, you can use this tool, or you can use Python for visualization. So we can change the number of neighbors, which means it will show more points. And let's say let's check for cat. So I don't think they have this word. So we can football, check for football. So by this you can convert it into 3D space, and for only for similar words. So you can search word here, and you can also check the similarity, and you can check full data from here. You can check for 10,000 for here, and you can use TSNE and many more dimensionality reduction technique. So this is how word embedding revolutionized NLP by providing dense vector representation of words, and Word2Vec based on continuous bag of word and skipgram effectively captures word meaning and relationships. By training custom embeddings, you can enhance NLP application for your specific task. So we have what we have seen in this video is we have covered this topic: word embeddings, what are word embedding definition, and how they are used in NLP, and Word2Vec. We have seen the code implementation, then we have visualized them 3D. So this was the video, guys. If you found this video helpful, please like and subscribe and share. So that's it for the video, and thanks for watching.